The theoretical conditions for tornadoes of intensity beyond EF5 exist. Supercells with extreme instability, ideal wind shear, and sufficient heat could, in theory, generate something that no known human structure would survive. It is a level without a name, and we hope we never have to give it one. The tornado scale exists because humans need to categorize in order to understand. Naming the danger is the first step toward learning to survive it. But what the history of the most intense tornadoes ever recorded reveals is that nature tends to outgrow the categories we create for it. Each level on the scale represents not just a wind intensity, but an implicit philosophy. The belief that a limit exists, that the limit can be measured, and that we can prepare for it. EF5 was conceived as the ceiling because the probability of something more intense was considered astronomically low. Nature has the inconvenient habit of ignoring probability. And what looks small today in EF0, passing through a sleeping town, may be the precursor to something no one has yet found words to describe. Wind speeds, measured at the edges of the funnel, reached 200 mph, and at the center, instruments simply fail, destroyed before they can transmit any data. And this is where the story should end, but it doesn't. The Enhanced Fujita Scale has no EF6. It ends at EF5, defined as any tornado with winds above 200 mph, with no upper ceiling on that definition. Anything beyond that is simply called EF5. The problem is that researchers analyzing damage patterns from historically devastating tornadoes have found evidence of winds that likely exceeded 300 mph in extreme cases. The Reno, Oklahoma tornado of 2013 was the widest ever recorded 2.6 miles across, and Doppler radar analysis measured gusts that produced destruction inconsistent with any standard EF5. Meteorologists have debated, in peer-reviewed publications, the need to expand the scale. Not because EF6 tornadoes are common, they may never have occurred in all of recorded human history, but because the absence of a category for extreme events creates a real problem in communication and risk management. If an EF5 with 205 mph winds and an EF5 with 305 mph winds carry the same label, how do authorities communicate the differential danger? How do you design a shelter for something that has no name? The seventh level isn't on the scale. But atmospheric physics doesn't care about that. Heavy vehicles are thrown more than 100 meters. Steel structures bend like wet paper. Thick-trunked trees aren't merely knocked over, they are stripped of all their bark by the violent friction of moving air. EF4 tornadoes represent less than 1% of all recorded events, yet they account for a disproportionate share of tornado-related deaths and destruction. Aerial footage taken days after an EF4 shows something deeply disorienting. City blocks where there is no longer any reference point that homes ever existed, as if the Earth had simply forgotten it was once inhabited. And then we reach EF5, winds above 200 mph, the official ceiling of the Enhanced Fujita Scale, the point where meteorologists, engineers, and researchers agree this shouldn't happen often, and yet it does. An EF5 doesn't destroy, it erases. Reinforced concrete structures are reduced to fragments. Underground shelters that weren't built deep enough fail. The ground along the tornado's path is literally stripped bare, no vegetation, no structure, nothing to suggest what existed there hours before. The Joplin, Missouri tornado of 2011 is one of the most documented EF5s in history. It killed 158 people, completely destroyed a functioning hospital, and traveled more than 22 miles. These are events that wipe out entire neighborhoods in minutes, and they're common enough that a whole generation of people has already survived one. Moving further up the scale, we reach EF3 with winds of 136 to 165 mph, and here the phrase "nothing is left" starts to become literal. And EF3 doesn't just destroy houses, it dismantles them, carries the fragments, and deposits them hundreds of meters away. Brick and mortar structures, which many people intuitively consider safer than wooden ones, suffer catastrophic damage. Exterior walls collapse. Concrete slabs are ripped free. Cars are thrown dozens of meters as if they were empty tin cans. What makes EF3 particularly unsettling is the random pattern of its destruction. Within the same city block, one house is reduced to rubble while another, just a few meters away, loses only its roof. That randomness makes survival patterns impossible to predict and difficult to explain to the victims. Survivors consistently report that the entire event lasted seconds. Seconds that permanently restructured their lives. The EF4, with winds of 166 to 200 mph, demands a new vocabulary to describe. Well-built houses with deep foundations are literally ripped from their slabs. What remains isn't a ruin, it's an empty lot, with only the concrete foundation as evidence that something once stood there. Close behind comes the EF1, with winds of 86 to 110 mph, and with it something that should sound like a paradox. The everyday tornado that shouldn't be everyday. Windows explode, cars are dragged, entire roofs are lifted away, mobile homes vanish. It's powerful enough to kill, but frequent enough that some regions develop a kind of cultural tolerance to the risk. People living in high-incidence zones build routines around the danger: underground shelters, community sirens, a background anxiety that never fully fades. The EF1 is the level where nature begins to demonstrate, without ceremony, that our physical structures are temporary. But it's at EF2, with winds of 135 mph, that the scale starts to impress even those who've heard about tornadoes before. Trees are uprooted entirely, wooden homes are destroyed completely, heavy vehicles are lifted off the ground, and ordinary objects, bricks, timber, tools become projectiles, moving fast enough to punch through walls. This is also where the tornado becomes more visible and terrifying in its form. The rotating air column, the iconic funnel, the low and constant roar that survivors always describe in the same way, as if only one phrase exists for it: a freight train coming. More than 25% of tornadoes recorded in the United States reach EF2. There is a scale to measure tornadoes. It runs from EF0 to EF5. Most people assume EF5 is the limit, the top, the worst nature can do. For a long time, that's what scientists believed too. They were wrong. Not completely, but enough that the story of the world's most extreme tornadoes is scarier, stranger, and more fascinating than any official scale can capture. Because nature doesn't read manuals. And when it decides to push past the boundaries of what has been cataloged, what happens defies not just buildings and cities, but the human capacity to comprehend destruction itself. It all starts with EF0, and here lies the first mistake. Winds between 65 and 85 mph. Sounds dangerous. It is. Sounds deadly? It can be. But within the scale, EF0 is treated as the lesser evil, enough to knock down branches, tear off roof tiles, and flip road signs. The problem isn't its intensity, it's how often it occurs. EF0 tornadoes are so common they become nearly invisible in the grand narratives about natural disasters. But common doesn't mean harmless. An EF0 moving through a dense urban area with old trees and poorly maintained structures causes damage wildly disproportionate to its modest place on the scale. And many tornadoes begin exactly this way, as EF0s, before intensifying within seconds. Underestimation is the real danger here.